Today we're going to be talking about exponential growth and decay. I think many of us already are fairly familiar with exponential growth and decay, but our goal with this is to establish exponential growth and decay as a differential equation. Okay, and with the establishing of the differential equation is like how do we model growth or decay with a DE? And that's the basic question we want to answer. So our main objective today is, again, modeling. All right, so the actual solution methods we use aren't really going to be really deep, but we can already guess at the answer. The answer is going to be, of course, an exponential. But we want to just see how we can use modeling to establish a differential equation. And I think when we go through this exercise, it'll become much more insightful how we can model a great many other things once we study this really seminal type of model. Okay, so we're going to talk about growth, in this case, as a population model. And really, what we have in mind is going to be like, bacterial growth. So the mental picture we have in our head, of course, is we have some sort of bacteria, and that after some amount of time going forward, all of a sudden there's a division, and then there, of course, are two bacterias. All right, and of course, if we keep going in time forward, after maybe some delta t time, and then there's another delta t time, there might be, of course, a death, and maybe for a different individual within our population, of course, there's more growth, like so. All right, so if this is the basic picture we have of how bacterial growth occurs, if I were to say, and I'm going to define P of t to be that the population at time t, okay, and time will be in some units, and we'll pick some units in a second. But maybe if I go down to if I look, so I can think of population as a function of time on this axis and then time on that axis. And maybe if I was going to go look over, a second. Now, of course, we're talking about a large, maybe a moderate-sized population of bacteria. You can expect the population, there'll be a division, and it'll be a jump. You wait a little while, and there'll be another jump, maybe jumps that are really fast. Maybe there's a death, maybe two deaths, then a jump back up, and so on and so forth. Like that, right? So obviously, what we're mentioning there is that basically, birth and death are discrete events. Okay, so they're discrete events. So how are we going to use differential equations to model this kind of thing? So clearly, modeling this as discrete events would be very hard. But maybe what we should do then is sort of pan out a bit. So what if I were to take the same picture, but now plot P of t over maybe a minute? Of course, all those little discrete events are still there. But you can sort of see that the discrete little jumps start to sort of look a little less jagged, and you can see there's more of a trend line going through it all. And of course, if we go to even wider time scale, maybe hour, for example, and again, we're just sort of doing a mental scenario here. The idea is that eventually those little discrete events don't show up anymore. Maybe if you focus in really closely on that, on a particular minute or a particular second, you might be able to see this sort of behavior. And if you focus in even more, but over the longer time scale, you know, it looks smooth. So we can essentially treat our model as a continuous model. We don't have to think of things as purely discrete events. All right. So okay, let's now do another thing. So let's suppose this petri dish. I probably spelled that wrong. Has constant conditions. All right, so what we're saying is we're setting up an experiment here with these bacteria where nothing, over time, nothing's changing. So what we're really saying is this is an autonomous system. All right, and that means that the differential equation we're going to come up with is going to be something f of p, and basically no t involved. And and if we want to be a little bit more specific, what we're saying is that birth and death rates are constant. They don't change with time. Okay, so now let's do our modeling here. So we're actually going to now define beta to be our birth rate. And okay, and we're going to use units of 1 over time. So you can pick your favorite units. We picked the units that are appropriate for our problem. You know, we could pick t to be hours in this case, for example. Okay, so it could be 1 hour. T is in hours. All right, and then also delta will be our death rate. And that's also going to be units 1 over time. Okay, so one question is, why is it 1 over time? Why is it not population over time, you know, number of individuals over time? And we'll get to that in a second. So now, of course, what we have to do is do some over some small time window. And I'll say delta t. We expect at least on average the number of births to be approximately, and I'll put this number of births is going to be equal to, and I'm going to put this approximately here. I'll make a little squiggly equal sign there. It's going to be approximately the birth rate times the number of individuals at a particular time when we start. Okay, a time window t, and I should put in here at time t, okay, times delta t. And again, we see here that the units do work out, right? So that's in units of 1 over time. This is in units of number of individuals. And this is in units of time. So of course the units of 1 over time and time cancel, and you're left with just number of individual. And of course on this side we also have number of individuals. So the units work out. Now likewise, I do the same thing for deaths, right? The number of deaths will be equal to some constant delta times, and this will be again approximate, delta times p of t times delta t. All right, so of course so the net change delta P, sorry, of the population, of course, is going to be births minus deaths. All right, so the kind of modeling we're doing here is very straightforward. Okay, we're just doing an accounting of the change in population, which is going to be births less deaths. Okay, of course, now we have expressions for both of those. So we're just going to put those in together. We'll call that beta minus delta times our P of t times delta t. Okay, right, so that's equal to delta P. All right, I'm going to do a little bit more. I'm going to actually just simplify my notation there. I'm going to call this beta minus delta. I'm going to call that K. So we have K times P times delta t. And then what, of course, I can do is divide by delta t. All right, in which case we get delta P. I should also put this approximate symbol here, of course, over delta t is approximately equal to K, which of course is the birth rate minus the death rate, times P. All right, so it's approximate because, of course, as we see right here with this equation, the number of births here, obviously the number of births will add to our population, but we're tracking over a small enough window of time that the number of individuals birthing at that time, of course, is incrementing up, but it's small relative to the total number that's there. Okay, so it shouldn't affect the birth rate. Won't be the total number of births will be approximately equal to this. All right, and of course, what we do then is make our time window smaller and smaller and smaller, and use the basic limiting operations of calculus to come up with our model dp dt is equal to kp. And now we set them equal because, of course, our approximation gets better and better and better if we go over a smaller and smaller window of time. All right, and of course, this is our classic. This is, of course, a differential equation. And we use basic modeling techniques of birth and death rates and doing a basic accounting of the number of births less deaths to come up with this great model for describing population growth or death. All right, so let's go to the next page here and write out our model. dp dt is equal to kp. So, of course, now we're going to use separation of variables. Okay, so we see here we can separate our variables. We have a dp 1 over p is equal to k dt. We integrate both sides, and we get natural log of the absolute value of p is equal to kt plus c. All right, so assume that p is greater than or equal to 0. All right, negative population makes no sense in this model. So in which case we can actually dispense with the absolute value symbols. Natural log of p is equal to kt plus c. And then, of course, we need to solve for p. We do so by exponentiating both sides. And we get p of t is equal to e to the kt plus c. That's all in the exponent there. But we can use the rule of exponents to go e to the c times e to the kt. All right, this parameter here, we can just relabel that to make it a little less messy and just call that a e to the kt. Now, okay, like any IVP, you're going to have some sort of initial condition. Call it P naught. So clearly we can see here that P of 0 is equal to a e to the 0, which is just a, which then is equal to that initial population. So after we just sort of relabel all of our letters, we can get to this final result. All right, so remember then, of course, that K was equal to beta minus delta, so the birth rate minus the death rate. So of course we have a couple scenarios here. One, of course, is k is greater than 0, and that means there's more births than deaths. And then we get exponential growth. All right, likewise, k equals 0, and that means equilibrium. In which case, p of t is just going to be p0 for all time, right? Likewise, k less than 0, we get decay. All right, and so that's pretty straightforward. We've probably all seen this before, but I hope we get a better appreciation for how the differential equation actually tells this story based on very simple accounting of births versus deaths over a short amount of time, and that leads us to a differential equation. And then the solution to that differential equation is the classic exponential growth model that I'm sure we've all used in various contexts over our education. So what the goal, of course, was to establish this whole process of growth and decay as fundamentally a differential equations type of modeling. Okay, so with this, let's do now an example. So let's talk about one more thing. So there we were talking about populations, but it's also this sort of growth death model can also describe chemical reactions. Okay, so for instance, if you have some sort of toxin, and then it has to be cleared from the body. Via enzymes or something like that. This can also be described as sort of a decay model. And to see how this would work, you understand that basically you have a bunch of toxins in your body, and then you have enzymes that are sitting around waiting to, and they're all diffusing around. So they're diffusing around inside the body, inside the bloodstream maybe. Everything's just moving left and right in a random Brownian motion. But eventually, sometimes they actually go together, and there's some random way that the enzymes will eat up the toxins, okay? And that, of course, the rate of clearance of the toxin should depend on the number of toxic molecules. Because essentially, and the idea is if there a lot of toxins, there's a higher likelihood that they will bump into an enzyme. Okay, and vice versa. And that of course can be described as follows. You can talk about the concentration C, or maybe of this chemical dt dt, or dc dt can be equal to negative k c, where k, I think of this as a rate constant, a sort of a reaction rate. I make it positive, and I just attach a negative sign, and that just helps me. I mean, I didn't have to do that. I could have made this a negative constant instead, but I made it a positive constant and use the negative sign just because I think it's more descriptive. It helps us understand a little bit more about what the model's saying. Okay, and of course we know that the solution C of t will be equal to whatever the initial amount of chemical there was in the body, and e to the negative kt is the solution, and you can get that adequately by just using separation of variables. All right, so of course we can do a model of this, and okay, and of course this model assumes that you know that this K reaction rate does not depend on time. Okay, later on we'll actually study when the reaction rate will depend on time, but we'll do that at a later date. So let's talk about a specific model. So we don't actually have to solve differential equations, but let's say that C at time 0 is equal to maybe 10 micrograms per liter of blood. Okay, so it's a concentration we're talking about. And let's say after t equals 2 hours, we observe that C of 2 is equal to 3 micrograms per liter. Okay, so obviously, and again, we'll assume that our reaction rate does not depend on time, that it's a constant reaction rate. Then we know then that we can write down the solution has to be of the form C0 e to the negative kt. All right, where now we already know what C0 is. It's 10 e to the negative kt. All right. So now the question is, what is the reaction rate? Okay, so we can find that easy enough. C at time 2, we know, was going to be equal to 3 micrograms per liter. All right, so we can write that in. That'll be 10 e to the negative k2. All right. We can do this a little further and go, that's going to be 3/10 is equal to e to the negative k times 2. Take a natural log of both sides, and we get natural log of 3 over 10 is equal to negative k2. All right, so now we need to solve for k, so of course what we do is we say k then is equal to negative 1/2 natural log of 3/10. All right. The next thing I need to do is I just want to simplify a bit more, and of course we know that there's the log rule. There's a log rule that says this: natural log of b times a is equal to the natural log of b to the a power. Okay, so we can do this: natural log of 3/10 to the negative 1/2 power. I want to simplify that a bit more and turn that into natural log of 10/3 square rooted. Okay, so that's the number we get out of it. And we can calculate that with a calculator if you want to get a decimal value, but that's an adequate result for us. So our k then is equal to natural log of the root 10 over 3. Okay, and that will be our reaction rate for this clearance of a toxin of some type. Okay, all right, so hopefully that gives you a clear understanding of how differential equations can describe this basic process of exponential growth and decay. All right, thank you very much.